So we'll just have a look at a few more and then some variations on that. So in the first 56 days of school, Samantha was late 14 times. So when we talk about her being late, it's 14 out of 56 days. Take the relative frequency as the probability she will be late. Now, in theory, the chances of you being late is a half a chance, because if you're not late, you're on time. But relative frequency is when we look back on the history of what's happened before and then make future judgments according to that. So, and I suppose in the case of attendance at school, rather than looking at the theory of being late and being on time, we do look at a student's record. So if they've been late quite a few times, there's a higher expectation they will be late. If they're never late, then there's a high expectation they will never be late. So it is the relative frequency you'd look at. Now, in 5 consecutive days, find the probability she will be late. Correct to 4 decimal places. Never, only once, more than once. Now, I know this sounds a bit strange, but we're going to call success being late. I know we don't associate being late with success, but it doesn't matter. It's in the eyes of maths. We're not making a judgment about whether it's good or bad. So the probability of success, so the probability of being late is 14 out of 56. And then this is a Bernoulli trial because you're either late or you're not late. So the not late is going to be the difference. So what's that? 42 out of 56. So in 5 consecutive days, so out of 5 days, find the probability she will be late never. Now, never late, well, then that would make that a 0. 5 choose 0. We would put down the probability of success, which in this case is late, but we're going to call it success. And then we write down failure. And then again, we use the formula from page 33. So the bottom number is going to be there, and 5 take 0 is 5. So into our calculators, we put 5 choose 0, which is 1. Anything to the power of 0 is 1. So really all we have to do is the 42 over 56, and we're going to raise that to the power of 5. So that ends up becoming 243 over 1024. Now, it does say correct to 4 decimal places, so we'll do that. 0.2373. So that's the answer to part 1. Part 2 says once only. So out of the 5 days, you're late once. So again, you write your success, you write your failure, and then you copy your formula. So your bottom number, and then the 5 take 1 goes there. So we have 5 choose 1 is 5. So that's the number itself. We have 14 over 56 because that's to the power of 1. And then we just need to raise the 42 over 56 to the power of 4. So that is 81 over 256. So we're going to multiply this together. And 81 over. So I'm just multiplying the 3 figures together. And I'm going to change that to a decimal, 0.3955 to 4 decimal places. So that's part 2. Now, what is the in 5 days, what's the probability she will be late more than once? Now, more than once would suggest twice, 3, 4, 5. Now, rather than going through all those, what I can do is I can take the 2 of these answers and add them, because this is the never and this is only once. So if I add the 2 of those together, that will cover never and only once. And then if I take that from 1, so if I take the never and only once away from 1, that should give me an answer of the more than once. Now you could go through the pain of doing, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5, but this is much easier and quicker. So 0.2373 added to 0.3955. So that ends up being 0.6328. Now, because that is the never and once only, when I do 1 minus that, we're looking at every other possibility, which is twice, being late twice or 3 times or 4 times. In other words, more than once. So 1 minus 0.6328. So, and as a decimal, 0.3672. So that's part 3. Let's have a quick look at 6. In a family of 6 children, what is the probability of having 3 girls and 3 boys? So we're going to call success having a girl, half a chance, and we're going to call failure not having a girl. Now, so from 6 children, what's the possibility of having 3 girls? We don't even need to talk about the boys, because if it's not a girl, it is a boy. So it's a Bernoulli trial. So we don't, once we consider one option, we don't need to think about the other. So we're going to write success here. We're going to write failure here. And then we're going to use our formula. So that's a 3 and that's a 3. So 6 choose 3 is 20. This is going to be 1/8 and this is going to be 1/8. So 20 times 1/8 times 1/8. And I end up getting 5/16. I can change that to a decimal, 0.3125. So that's our answer. And then we're asked, of 400 such families, how would you expect to have 3 girls and 3? How many would you expect to have 3 girls and 3 boys? So all I have to do now is multiply my answer by 400, because that should give me the chances of out of 400, and that's giving me 125. So in other words, we expect 125 families out of the 400 families. So in other words, we expect 5/16 of them to be like that, 3 girls and 3 boys. Now we'll just maybe jump down to 8. In Ireland, 40% of the cars are Japanese. So probability of success is being Japanese. Probability of failure is not being Japanese. So again, you can see the Bernoulli trial. I mean, there could be other types of cars, but we're not interested. We're just looking at Japanese or not. Okay, 10 pass. So we're talking 10 cars pass a point in Ireland randomly. What is the probability that exactly 4 are Japanese? So we do 10 choose 4. Success is 0.4. Failure is 0.6. Copy your formula from page 33. The 4 goes there, the 6 goes there, and then we just pop it into our calculator. So I'm just going to speed this up a little bit here. You can try it yourselves. Okay, so I am getting to 2 decimal places, 0.25. So I'm actually expecting a quarter of them to be a quarter of them, sorry, out of the 10 to be Japanese cars. Okay, yeah, so I'm going to leave that video there and I'll just do one more